Okay, let's dive in. We all sort of take Newton's third law of motion for granted, right? Action reaction, forces balance out. It feels like bedrock physics. But what if that rule sometimes gets bent, especially down at the microscopic level? Today we're looking at something really fascinating. How human sperm and other tiny swimmers like algae seem to almost defy this law. They move through fluids that, well, theoretically should stop them in their tracks. So our mission here is to unpack how scientists actually saw this happening, what's going on that allows it, and what it could mean for things like tiny robots or understanding nature better. And we're basing this on a great Science Alert piece looking at research from Kyoto University. So maybe let's start with the basics. Sir Isaac Newton, 1686, the famous laws of motion. We're focusing on number 3. For every action, there's an equal and opposite reaction. Simple collision, like two marbles hitting.
Exactly. That's the classic example. It implies this perfect symmetry, right? Forces always cancel out. They're always balanced.
Yeah, kind of cosmic neatness.
And it's incredibly fundamental. It explains so much about how the physical world works, from planets orbiting to just, standing on the ground.
Okay, but here's the twist. What if nature isn't always quite that neat and symmetrical, especially when things get messy or alive?
That's precisely it. We run into situations with what are called non-reciprocal interactions.
Non-reciprocal, so not equal and opposite.
Kind of. It shows up in these, let's call them unruly systems. Think about a flock of birds turning together or particles swirling in a liquid. And crucially for our topic, swimming sperm cells.
Okay.
These things, these modal agents, they move in ways where their interactions with their environment aren't perfectly mirrored. There's an asymmetry.
So how do they get away with that? Doesn't that violate the core law?
Well, the key, the sort of loophole, is that these agents generate their own energy. A bird flaps its wings, a sperm wiggles its tail. They're constantly putting energy into the system.
Ah, okay. It's not a closed system just reacting.
Exactly. This pushes the whole situation far from equilibrium. The nice, balanced rules of action-reaction don't fully capture what's happening anymore because there's this internal engine, this constant energy input driving the asymmetry.
Right, that makes sense. So someone actually figured this out specifically for sperm. How did they even observe that? This seems like where the Kyoto University team comes in. Kenta Ishimoto,
Yeah.
a mathematical scientist. Their study, sounds like it was published, October 2023?
That's the one. And their approach was quite clever.
What did they do?
They took existing experimental data on human sperm, like actual observations,
Yeah.
and analyzed it deeply.
Yeah.
But they also built computer models, specifically modeling the movement of a type of green algae called Chlamydomonas. It swims in a similar way.
Okay, similar how?
Both sperm and this algae, they use these thin, whip-like tails called flagella.
Right.
These flagella stick out from the cell body, and they bend and deform in these wave-like patterns to push the cell forward, like tiny biological motors.
Okay, but here's the bit I'm stuck on. Wouldn't swimming in something thick, like the fluids these cells are often in, just dampen everything? Like trying to wave your hand in honey, all that energy should just dissipate, shouldn't it?
Logically, yes, that's the paradox. Viscous fluid should sap the energy right out of that waving flagellum. You'd expect movement to be really hard, if not impossible.
But they move fine. So what's the secret?
Well, the researchers found the first key piece. These flagellas possess something they termed odd elasticity.
Odd elasticity. What makes it odd?
It's not just about being flexible. It's a specific property that allows the flagellum to move, to bend and unbend without losing as much energy to the surrounding fluid as you'd normally expect. It's almost like the fluid itself resists less when the flagellum moves in this particular odd way. It's a very specific kind of interaction.
Okay, so the material itself has a weird property that helps it cheat the viscosity, sort of?
In a way, yes. But even that odd elasticity didn't fully explain how the flagellum generated forward thrust from its waving motion. It explained the low energy loss, but not the effect of propulsion itself.
Ah, okay, so there was still a missing piece.
Right. So digging deeper with their models, they came up with a related but distinct concept, an odd elastic modulus.
Modulus. That sounds more technical.
It is. It basically describes the internal mechanics of the flagellum material itself, how forces within the flagellum work when it bends. This odd elastic modulus captures how these internal forces are, again, non-reciprocal and act over a distance within the flagellum.
So forces inside the tail are interacting weirdly.
Exactly. And that internal weirdness is what ultimately allows the tail's wave motion to effectively push against the fluid in a way that breaks that action-reaction symmetry with the fluid's resistance.
Wow. Okay, they actually quoted something specific in the article, didn't they?
They did. They said, from solvable simple models to biological flagellar waveforms for chlamydomonas and sperm cells, we study the odd bending modulus to decipher the non-local, non-reciprocal inner interactions within the material.
Right, non-local, non-reciprocal interactions. That sounds like the core of it. Forces inside acting strangely across distances.
Precisely. It's the internal physics enabling the external rule bending.
Okay, so sperm are exploiting weird internal physics to swim. Fascinating stuff. But why should you listening now really care about this? What's the bigger picture?
Well, the potential applications are actually pretty exciting. Think about designing tiny robots.
Microrobots.
Yeah, small, self-assembling robots that could navigate complex environments, maybe even inside the human body, for targeted therapies. Understanding how sperm moves so effectively gives us a blueprint.
So like building little machines that swim using this odd elasticity principle.
Potentially, yes. Or using these principles to design new kinds of active materials that can move or change shape on their own. And beyond robotics, the modeling methods they use could help us understand other complex systems better, like those bird flocks we mentioned, or other kinds of collective behavior where non-reciprocal interactions are at play.
Right. It's like finding a loophole in physics at the microscale could inspire totally new ways of thinking about engineering or even social dynamics, maybe.
It definitely opens doors. Nature's solutions are often way more sophisticated than our initial designs.
It really drives home how much we can learn from just observing life, even down to a single cell. These microscopic tricks could unlock big innovations. Okay, so let's just quickly recap. We've seen how human sperm, these tiny swimmers, manage to navigate thick fluids by essentially sidestepping Newton's third law. And the key seems to be these weird properties. Odd elasticity, reducing energy loss, and this odd elastic modulus, describing the strange internal forces that enable propulsion.
Right. It's a beautiful example of biology exploiting subtle physics.
It really is an aha moment, isn't it? Simple life processes hiding these deep physical secrets. Which leaves us with a pretty mind-bending final thought to chew on. If tiny biological things like sperm can operate outside the classical rules we thought were universal, what other fundamental laws might have subtle exceptions or bends in the incredibly complex systems of life at all sorts of scales?
Yeah, where else are these loopholes being exploited in ways we haven't even imagined yet?
What does that mean for our understanding of physics, biology, or even designing future tech inspired by life's ingenuity?
It's a big question.
Definitely something to keep pondering, stay curious, keep exploring these amazing intersections between biology and physics. There's clearly still so much to discover. Okay, let's dive in.